All right, good morning. Welcome back to the second week. We're going to just finish up with the dot product lecture. We just got into it on Friday's class, and now we'll go through some of the details of the dot product and finish that off. And then we'll likely get into another kind of product on three-dimensional vectors, and that is the cross product. So that's lecture 12.4. So where we got to last day was we started with this motivating problem of finding the angle between two vectors, A and B. And so there's just two arbitrary vectors sketched there. The angles identified between them. And the thing we're interested in is finding out what the measure of that angle is. Now, it's not quite clear with that motivating problem why it's even connected to the next statement, which is about the definition of the dot product of two vectors. But that's the thing we're going to make the connection. So what is the dot product of two vectors? Well, we defined on Friday that it's just the component-wise product and then added together. So we multiply the two x components, two y components, and the two z components for each of the vectors, and then sum them all up. And this can extend to any number of dimensions. So we can go to 4 dimensions or 5 dimensions and so on. I just wanted to mention, I just see the directed message to me in the chat from our TA. So I just wanted to mention that Nilufar will be moderating our discussions or our chats. So if you post something in the chat and you're afraid I'm not going to be able to see it or address it, not to worry, Nilufar is there and she'll be able to help you with any questions you have. So feel free to post questions in the chat. All right, so we covered an example, just a basic example of a dot product of two vectors, just to see what the mechanics are of actually computing it. And then we summarized some of the properties of the dot product. Now, all of these properties of the dot product follow immediately from just its definition, how it's defined in terms of the products of the components all summed together. So those properties are what we're going to be using whenever we need to do some algebra involving vectors and the dot product. For example, one of the ones that we'll be using or making extensive use of is the distributive property of the dot product over the sum, and that's the one that sort of indicated there with the distribution arrows happening. So it says if you've got the sum of two vectors and you want to take the dot product with another vector, a third vector, that you can compute the individual dot products and add their results. Okay, so then we get to the geometric interpretation. So why is this definition of the dot product related in any way, shape, or form to the angle between two vectors? And it turns out that this is really just a consequence of the Pythagorean theorem for right triangles. Pythagorean theorem is telling us the relationship between the lengths of the sides of a right triangle. More specifically, this is a consequence of the law of cosines, but the law of cosines is a direct result of the Pythagorean theorem. So what we'll do is we'll justify this result, and I'll also prove the law of cosines in the process, just in case you may have forgotten the law of cosines or may have forgotten why the law of cosines is true. So let's go ahead and look at a couple of the vectors drawn here. So we've got an A vector and a B vector. And we're going to draw in here this vector, which goes from the tip of A to the tip of B, or in other words, the vector whose tip is B and whose tail is A. So if I want to label that vector, what I can do is I can just label it as the vector B minus A. And so we've got this picture here. And what I want to do is I want to just take this triangle and work out how the lengths all relate to each other. Now, this isn't a right triangle, but for triangles that are not right triangles, that don't contain a right angle, we have the law of cosines that allow us to relate all of their side lengths. So what we have is that the law of cosines says the following. If I've identified an angle I'm interested in, which in the diagram is that angle theta, then it says the length of the side opposite theta, the square of that is equal to the sum of the squares of the other two sides minus twice the length of the other two sides times the cosine of the angle between them. So that's the law of cosines, but just written in the form of where our sides are given by vectors. So we're using magnitudes or lengths of these vectors in this case. Okay, so at this point, I don't want to just sort of say, well, here's the law of cosines, and then voila, here comes the formula for the dot product equal to the magnitude of the vectors times cosine of the angle between them, because they're going to follow directly from this. Instead, what I want to do is I want to make sure we're all on the same page. So let's go back and give a proof of the law of cosines, just so we can see why this geometric interpretation is true from basic principles. So nothing's left out in our argument. So what we're going to do is we're going to draw a triangle, but I'm going to draw it like this. I'm going to stick it, well, maybe I'll try to make it so it doesn't look like a right triangle. So maybe something like this here. And let's let this be side length A. Down here is side length B, and there is side length C. And then we've got this angle here, the angle theta. I'll try to squeeze in there, angle theta. Okay. So now what I want to do from this picture is I want to come up with a relationship between all the sides. And that's our law of cosines, is how do the lengths of the sides all compare to each other. So in order to do that, what I'm going to do is I'm going to drop a perpendicular down from that top vertex, or that top point of the triangle. And now I've got two right triangles in my picture. And those two right triangles in my picture I can use the Pythagorean theorem on. So let's call this triangle 1, and we'll call this one triangle 2. So by Pythagorean theorem on triangle 2, what we have is, well, the hypotenuse is c, so I have that c squared is equal to the height squared times the base squared. And so now I have to think, what is the height? Well, the height is the length of that purple line segment. But I can get that height by looking at triangle 1. Triangle 1, I've got the hypotenuse A, so I know what its height is. It's going to be A sine theta. So it's going to be the height of that purple line segment is A sine theta, and that's all squared, plus, now I need to know the base of triangle 2. What is the base of triangle 2? The base of triangle 2 is this distance here, that distance there, and that distance is obtained by taking this distance here, the base of the triangle 1, and taking it away from the base of the whole triangle. So what we get in this case is the base of triangle 2 is the full length B minus the base of the triangle 1, which was A cosine of theta. So there is our Pythagorean theorem applied to triangle 2, where we used triangle 1 to get a couple of important distances that we needed. And this is just the law of cosines now. That statement there is what we call the law of cosines. We can just rearrange it a little bit. So this becomes a squared sine squared theta plus we get a b squared, we get a minus 2ab cos theta. That's our cross term. So now you can sort of see where that 2ab cos theta is coming from in our law of cosines on the left. And then we've got a plus a squared cos squared theta. So that's just expanding everything out. And now I notice that this term and this term add together, and we get a sine squared plus a cos squared, so that's equal to 1. So this becomes c squared is equal to a squared plus b squared minus 2ab cos theta. And so there is our proof of our law of cosines. It comes from just drawing the appropriate picture in the coordinate plane, which is that triangle I drew above, and then using the Pythagorean theorem on the two triangles to piece things together. Okay, so there's our law of cosines for our triangle on the left now. And now what we want to do is go ahead and see, if we start to simplify this, why it turns into that geometric interpretation statement I've written above. A dot b is equal to the length of the two vectors times the cosine of the angle between them. So what I need to do is I need to take the length of b minus a and square it. Now, I'm not going to take the length of b minus a and square it. In other words, I'm not going to work with components of these vectors. What I am going to do is notice that the length of b minus a squared is just the dot product of b minus a with itself. So this is b minus a dotted with b minus a. That's what the square of the magnitude of a vector is. It's just the vector dotted with itself squared. I'm going to scroll back up and see, didn't actually write it down anywhere, but we can see it from here. That notice that what we end up getting is, or for a special case, we get the dot product of a vector with itself is a1 squared plus a2 squared plus a3 squared. And so that means that if I was to take the absolute value of that and then square root it, in this case I don't need to take the absolute value because it's positive. So if I was to square root this thing, what I get is the square root of the sums of squares, which is just the length of a. So this is the property we're using. Now we're just saying, okay, so then a dot a is equal to the length of a squared. That's the property we're going to use here. Whenever I see a magnitude squared, I can replace it with a dot product of a vector with itself, or whenever I see a dot product of a vector with itself, I can replace it with a magnitude squared. Okay, so we've got, that's our first step. Then we've got here we've got our magnitude of a squared plus our magnitude of b squared minus our 2ab cos theta. And now with the dot product, I'll use the distributive property. And I can distribute, basically I can distribute everything. I can distribute the b minus a over the one on the left. I'll leave the details for you to sort of think about. What I end up getting is I get a b dot b, and then I get a minus a b dot a, and then I get a minus an a dot b, and then I get a plus a dot a. And that's still equal to the stuff on the right-hand side. Okay, so we've done this distribution of these differences and the dot product. Now at this point, we want to see, do we get some cancellations? Well, the idea is, yeah, we do, because as we saw, the connection with the dot product and the magnitude is that this is equal to the magnitude of A squared, and this is equal to the magnitude of B squared. And the two things that are left over in the middle there is just twice the A dot B. So what I end up getting is I get that this term cancels with this term cancels with this, and I get a negative 2A dot B is equal to a negative 2 magnitude of A magnitude of B cosine theta. And so now I can cancel off the negative 2 on both sides by dividing both sides by negative 2, and we get our result. A dot B is equal to magnitude of A magnitude of B cosine theta. And so that's what we wanted to prove. So we define the dot product to be the product of the components all added together. And it turns out that under that definition of how to combine two vectors into a scalar, that it's related to the cosine of the angle between them through the law of cosines. So this is quite nice because now it tells us that for any two vectors, we have a way of constructing the angle or determining the angle between them. And I do want to add that this is not just restricted to 3 dimensions. This is true no matter what dimensions your vectors are in. It could be higher dimensions, 4, 5, 6 dimensional vectors. You can get the angle between them by computing the dot product in this way. For us, we'll be mostly focused in 3 dimensions. Okay, so let's find the angle. We'll do an example here. Find the angle between these two vectors. So what we have to do is we compute the dot product of them, A dot B, and then also divide by their lengths. So this is going to be 0 plus 0 plus 12 is the dot product, and the lengths are 9 plus 16 and 16 plus 9, or in other words 12 over the square root of 25 times the square root of 25, or 12/25, which means that the angle between them is arc cosine, or in other words cos inverse of 12 over 25. And this is about 1.07 radians, which is about 61.32 degrees. Okay, so that's how we effectively use the dot product to compute the angle between two vectors. One thing I want to just point out is that the angle between two vectors is a value between 0 and pi. So this might be worth noting out that you want to note that theta is a value between 0 and pi. So the angle between two vectors, if I have two vectors here, the main point is you can sort of think of there being two angles. There's the angle, the shortest way to go from one vector to the other, or the longer way. And the angle for us is always going to be the short way. It's the angle between 0 and pi. Okay, so what else do we get? Well, the dot product gives us a nice way to check whether two vectors are perpendicular or not. Because we can just work out the dot product. If the dot product is 0, we know the two vectors are perpendicular. This is going to come in very handy over the course of this term. We're going to be using this all the time. So what, or maybe I should say, why is this true? Well, two vectors are perpendicular, so that little upside down T represents the perpendicular. So A is perpendicular to B, if and only if. Well, what does the angle have to be? If two vectors are perpendicular to each other, then the angle between them, in this case, again, the angle we're talking about is the angle between two vectors, which is between 0 and pi. So the angle, yeah, it has to be 90 degrees or pi by 2. So theta has to be pi by 2. But if theta is pi by 2, then that means the cosine of theta must be 0, because cosine of pi by 2 is 0. But the cosine of the angle between two vectors is 0 precisely when the dot product of two vectors is 0. That was our main result. We just proved the connection between the dot product and the cosine. And so that means that two vectors are perpendicular precisely when their dot product is 0. So let's check, see how we can use this as a check. Let's check that these two vectors in 3 dimensions are perpendicular to each other. So go ahead and do a quick calculation and let me know in the chat if you think they're perpendicular or not. What do we think? Are these two vectors perpendicular? Yep, good. We've got a lot of confirmations about them being perpendicular, so let's see why. So we're going to compute the dot product, so that'll be 3 times 2 plus 4 times -4 plus 5 times 2. So that's 6 minus 16 plus 10, which is 0. So that means that A is perpendicular to B. Yeah, so it's a very nice result to have, in the sense that if I want to know whether two vectors are perpendicular or not, it's just a very simple, in some sense, straightforward arithmetic calculation of just some products and some sums. I don't actually have to work out any angles in this case. I don't have to work out an angle in particular. I just need to work out a dot product. All right, let's go ahead and look at another topic related to this, and this is known as direction angles. So for a given vector in space, there are some special angles for that vector, and I'll just draw an arbitrary vector in here, maybe something that looks like this. So for that vector in space, there are some special angles to note. Let's put them in some colors here. So the first angle is the angle that that vector makes with the positive x-axis. That's what we're going to call angle alpha. We could also look at the angle between that vector and the positive y-axis. That's what we'll call angle beta. And we could also look at the angle between that vector and the positive z-axis. That's what we're going to call gamma. And those 3 angles are enough to determine the direction of that vector. Doesn't determine the magnitude, but it does tell me the vector's direction. And these are known as the direction angles. So these 3 values give us the direction of our vector. So the next problem is asking, if I know the direction angles of our vector, can we find the components of our vector? So if I consider alpha, alpha is the direction, or the angle that V makes with the positive x-axis. But instead of talking about positive x-axis, positive y-axis, positive z-axis, what I should instead be talking about is the vectors that are in those directions. So that's I hat, j hat, and k hat. Those were those standard basis vectors we talked about before. So what is alpha? Alpha is the angle between V and I hat. So what that means is that V dot I hat is equal to the length of V times the length of I hat times the cosine of the angle between them, but that angle is alpha. So that's how we can find alpha from our vectors, or in other words, that's how alpha determines the direction of our vector v, or at least part of our direction of our vector v. In particular, what is this going to do? Well, v dot I hat is just going to strip off the first component of v, and the magnitude of I hat is 1. So we get this, that the magnitude of v times cosine of alpha gives me the first component of our vector v. We can do the same thing for beta. V dot j hat is equal to the length of v times the length of j hat cosine of the angle between them, or in other words, the second component of v is the magnitude of v times cosine of beta. And lastly, doing the same thing with k hat, or the third component, we get this expression. And so v3 is equal to the magnitude of v times cosine of gamma. And that means then that v, which is the vector v1, v2, v3, is equal to the magnitude of v times cosine alpha, the magnitude of v times cosine beta, and the magnitude of v times cosine gamma. Or in other words, I can factor out that scalar value, which is the magnitude of v, and I get cosine alpha, cosine beta, and cosine gamma. And so our observation here is that once I know the direction angles, which are alpha, beta, and gamma, then that gives me a unit vector that points in the direction of v. So this is by taking the cosines. So this is sorry, I spelled the word unit wrong. This is a unit vector in the direction of v. So that's how we can, sorry, I'm just catching up on the chats here. Shouldn't we have an arrow sign at the 2 of A and B? Sorry, I'm missing where the arrow sign is. There should be one here on this V. Number 9.
Hey, Jimmy, that's for number 9.
Number 9. Sorry, I'm still getting there. Number 9. Okay. So shouldn't we have an arrow sign? Are we talking above the A and the B? So here? Was that the question?
That's correct, yes.
Yes. Yeah. Perfect. Thank you. Yeah, there should be arrows there. I think what I had in the notes are those are actually boldface A's and B's, but they don't really come out very well. So yeah, I should actually just use arrows in all cases rather than bold letters in typefaced text. Thanks for pointing that out. Okay, so what we have is that when we know the direction vectors, or sorry, the direction angles, we can take the cosines of them and put them together to form a unit vector in the direction given by those angles. And so then multiplying by the magnitude of the vector v gives us our representation of a vector. So now let's find the direction angles for this given vector here. So the direction angles, I'm just going to highlight it's really these equations that give us our direction angles. So for example, b, the magnitude of b is given by 2 squared plus negative 4 squared, which is 16, plus another 2 squared. So that's root 24, or in other words, 2 root 6. So that's our magnitude. And then we have that cosine of the first direction angle is going to be b1 over the magnitude of b, or 2 over 2 root 6, or in other words, 1 over root 6, which means that theta is equal to arc cosine of 1 over root 6. For cos beta, we get that as b2 over the magnitude of b, or in other words, negative 4 over 2 root 6, or negative 2 over root 6, which implies that beta is equal to arc cos of negative 2 over root 6. And cos gamma is b3 over the magnitude of b, or 2 over 2 root 6, which is 1 over root 6, which tells me that gamma is equal to arc cos of 2 over root 6. And so there are the corresponding direction angles. Okay, so these direction angles just give us one way to work with the components of a given vector. To be honest, it's going to be quite rare where we actually work with these direction angles. You know, I'm trying to think off the top of my head of maybe more than 1 or 2 places where we actually work with them, but it's quite rare. But it's good to know that we can describe the direction of a vector just by the angle it makes with the I, j, and k hats. Absolutely. You could also find the unit vector in the direction of b. So that's a good point, Nosa. Yeah, if you can find the unit vector in the direction of b, let's actually do that. So that's a good comment. This is an, I'll say, alternate solution. So if we found the unit vector in the direction of b, which is b divided by 2 root 6, so I'll divide that into each of them. So that's 1 over root 6, negative 2 over root 6, and 1 over root 6. Hopefully we're still on the page. Yep, good. You can still see it. And then we know that this is cosine alpha, this is cosine of beta, and that is cosine of gamma. So that means that alpha is equal to arc cos of 1 over root 6. Beta is arc cos of negative 2 over root 6. And gamma is arc cos of 1 over root 6. Yeah, exactly. So you can make the connection with the unit vectors and work with them that way. As you know, the components of the unit vector have to be the cosine of the direction angles, or in other words, the direction cosines. All right. Next, we will look at projections. So both a scalar projection and a vector projection. So there's a couple of formulas there. I'm not going to talk about the formulas just yet. I'm going to work with the idea of what we're trying to capture here, and then we'll see how the formulas just sort of pop out from this. So here's our idea. We've got 2 vectors. We've got a vector A and a vector B. And what we'd like to do is, so once I sketch them in here, doesn't matter really how they're situated in space, but I'll draw them this way just sort of easier to visualize what's going on if I just reorient my vision so that the A is going horizontally and then the B is just going up from there. So once I have this sort of picture drawn, what I could ask is, you know, how much of B is pointing in the same direction of A? That's equivalent to sort of saying, if I was to take B and look at the shadow that it casts on A, if I was to shine a light in some sense from above, then what I get is, I get that, you know, this pink vector sort of represents how much B is pointing in the direction of A. And that's what we're going to call the projection of B onto A. So I'll call this pink one the projection of vector B, and then we use a little subscript with the vector A. That's the vector we want to find. So we already know its direction. Its direction is A. Its direction is in the same direction as A. But we'd like to know what its length is, or its magnitude. And that's what these formulas up above are capturing, but we're going to work these out. Okay, so what do I want to do here? Well, I want to say that this projection of B onto A, I already know it's in the direction of A. So I know it's going to be some constant, let's say C, times the vector A. It's a scalar multiple of A, the vector A, because they are parallel to each other. They point in the same direction. And so it's going to be some positive number C times the vector A. Then what I could do is I could say, well, it breaks up, B can then break up into two different vectors. I can write it as a sum. It's the sum of the projection vector plus this other green vector. What's the green vector? Well, the green vector is going to be B minus the projection vector, but we'll get that relationship in a second. I'll just call it something. I'll call it W. And so what we have from this is that B is equal to, well, it can be obtained by taking the projection vector and adding that to W. The projection vector, which we've just called C times A, can replace that projection vector, in which case we get this equation. So that's just an equation that represents that triangle in the picture, the pink, the green, and the blue vectors. Now what I'd like to do is I'd like to try to find out what the value of C is. That's ultimately my goal. I know that the projection is going to be a multiple of A. The question is, what's that multiple? How big is C? And that's a measure of how much B pointed in the same direction as A. So the way we're going to do this is we're going to try to get rid of stuff. And the one thing I know that I can get rid of is if I have a vector that's perpendicular to another vector, when I take their dot product, I get 0. So that's my key observation here, is that I can get rid of that W by taking a dot product of W with A, because they are perpendicular. So what I will do is I will dot with vector A, and I'll do that to both sides. So we'll go A dot B on the left, and I will take the dot product with A on the right. So A dot this whole thing. And then I will use the distributive property to distribute the dot product, and then I'll use one of those properties that allows me to just pull the constant out front in that first one, plus A dot W. That's equal to A dot B. The reason I've done this is because this is 0. A dot W is 0 since A is perpendicular to W. All right, that's how we define W. We first found the projection of B onto A, and so then when we took B minus that, we got a vector that was perpendicular to A, which we called W. And so that means then that we've got an equation which we can now solve for C. C is equal to A dot B over A dot A. I'll just continue this on over here. So that means that C is equal to A dot B over, and the dot product of a vector with itself is just its magnitude squared. And so that's the value of that constant C. The value of that constant C is this quantity here. And so that means then we have that the projection of B onto A is given by this quantity C, which we've now computed. We now know this value times A, like this. Now the thing is that this writing the projection in this way, I want to try to figure out how much of B points in the same direction of A. So I really want to know how long that projection vector, that pink vector is, how long it is. But the way it's written right now, C times A, the length of it is the length of A times the magnitude of C. I don't want it to be, muddled with the length of A. I don't want the length of A to influence how long that projection vector is. So what I have to do is I have to just think, what if I did these calculations for a unit vector in the direction of A? In other words, everywhere I see an A, I'd really like to have it as A over the magnitude. So that's the next step I'm going to make, is I'm just going to write it as this, where I'm only going to keep only one of those lengths, and I'm going to move the other one out here. And so now, that's not a dot because this first thing's a scalar, so maybe I'll just put some brackets in here. I'll put the brackets on the other thing. So now what we have is that the projection of B in the direction of A is given by this scalar multiple of a unit vector. So now I'm looking at the length of the projection of B onto A. That's the length now, because it's the scalar times a unit vector. And that length is what we're going to call the component of B in the direction of A. So that's this piece now. We've just proven that piece. The component of B in the direction of A is basically how much of, or what's the length of, the part of B that points in the same direction that A points in. And that's that, A dot B over the length of A. Sometimes I like to write it like this, A over the magnitude of A dot B. So I like to just move that length of A underneath the vector A itself, because now this is a unit vector. And so what this says is that in order to figure out how much of B points in the direction of A, I just need to have a unit vector that's in the direction of A. So get rid of all of those lengths that are going to crop up from that one, because I don't want to consider how long A is. I just want to know its direction. So first normalize A. Once you've done that, you now know the direction that you want to find things pointing in, and you just dot it. You just dot it with B. And so that's telling me then, this formula here is telling me that the dot product is a quantity that tells you how much of one vector is pointing in the direction of another vector. The projection vector itself, we already worked out. We got it here. And so we've proven that one as well. So really, we got the projection vector first, and then we had to adjust by lengths in order to figure out what the appropriate quantity was for the component of B in direction of A. And we've got that. So this tells us that the dot product is really a measure of how much two vectors are pointing in the same direction. Okay, so let's find the scalar projection of B onto A for these particular vectors. So we want to find both the scalar and the vector. So we'll go for the scalar first. The component of B in the direction of A is A dot B over the magnitude of A. A dot B is 6 minus 2 plus 4. And then the magnitude of A. That is 4 plus 1 plus 1 square rooted, or in other words, 8 over root 6. So that's how much of B is pointing in the direction of A. And then we've got to work out the projection vector. Now we could try to do the same calculation again, or one thing we can note is that the projection vector is, since I already worked this value out, it's the component of B in the direction of A times the unit vector in the direction of A. That's just sort of moving one of those magnitudes underneath A. And so that means that we can work it out as, I'll write it down here, component of B in the direction of A times A over the magnitude of A, which is equal to A over root 6 times the vector A, 2, 1, 1, And then we've also going to divide by the length of that, which is another 1 over root 6. So this is 8 over 6, 2, 1, 1, or in other words, 4/3, 2, 1, 1. And so there is our projection of B into the direction of A. So it's a vector that points in the same direction of A, but it's basically the shadow that B is casting on it. So again, always good to have these pictures in mind. There's A, there is B. What we just worked out is this vector here. And actually, I should have redrawn my picture because I'm looking at it. 4/3 is bigger than 1. So what we really have is A, and then B is looking like this. And then our projection vector is longer than A itself. And that's the one we worked out. Okay, so that's the dot product. That wraps up everything we need to know for this week's assignment. So you've got all the information, we've covered all the sections. So you can now feel free, if you haven't done some of the stuff on dot product, feel free to go and do that. You've now got the tools. What I want to touch on just in the last 2 minutes is the other product. The other product that we're going to be interested in, which is the next lecture, is the cross product. Much like the dot product was sort of tied in with the angle between two vectors, we took that as sort of a motivating problem and then showed how defining this product in some sort of funny way, the product of the components all added together, that actually was the thing we needed to work out the angle between two vectors. In the situation of the cross product, there's a similar motivating problem, and that is finding the area of the parallelogram from between two vectors. So for example, I've got two vectors that look like this. I could be interested in what the angle is of what the area is of the parallelogram that they form. So there's the parallelogram that they form, and I could be interested in what this area is. Now, what we do know about areas is that if I knew how tall, like I know the area of a rectangle, so I can always just sort of take this thing and turn these things into right angles just by shifting everything across. And that gives, I mean, this is something you did in calculus 2 when you worked out areas of various regions, is you realized that it was just the integral along the vertical direction, if you will. And since all of those things had the same lengths, that it was equivalent to the area of a corresponding rectangle of a particular height and a particular base. So in this case, our height, if this is B and this is angle theta, our height in this case is B sine theta. And if this is vector A, then our width of our parallelogram in this case is the length of A. And so we know that the area is the length of A times the length of B times sine of the angle between them. And this is all well and good if we can work out the sine of the angle between them, which we can use the dot product to find the cosine of the angle between them, and then therefore sort of work out the sine of the angle between them. This kind of looks like the formula for the dot product, except the sine is replacing the cosine of the angle. But it turns out that this quantity is actually related to another product, not the dot product, but it's more closely related to what we call the cross product of two vectors. And the cross product is two vectors are involved in the product, and a vector is the output, as opposed to the dot product, which produced a scalar. And so the cross product is given by this formula here, where you take the components of the vectors A and B, and you create a new vector with these three components, and you obtain it by multiplying the various components in this sort of funny way. And we'll talk about how to think about this product and the properties it has next day. So that's for next class. We will get into the cross product and all of the geometry around it. So that's it for today.